In this video I'm going to talk about the sum of the Fibonacci numbers with even indices. The Fibonacci numbers are defined recurrently like this. So we set f1 and f2 to 1, and then we have this recurrent relation that says that the next Fibonacci number is equal to the sum of the two previous ones. In one of the previous videos I proved an identity that the sum of the first n Fibonacci numbers can be expressed as one of the other Fibonacci numbers, and then there was another video where I proved an identity about the sum of first n Fibonacci numbers with odd indices. And now, so in this video I'm going to prove that the sum of the first n Fibonacci numbers with even indices. So I'm going to consider this sum and to prove that it's equal to f2n plus 1 minus 1. Okay, so the proof is going to be by induction. By induction, so the base case for n equal to 1 should be trivial. So on the left side we have f2. We need to verify that this is equal to f3 is equal to f3 minus 1, right? So f2 is equal to 1. By definition, f3 is equal to f1 plus f2, which is equal to 1 plus 1 and equal to 2. So therefore the right side is equal to 2 minus 1 is equal to 1. Okay, so the left side and the right side are the same, therefore the equality holds. So now the inductive step. So we suppose that the equality holds for n. Suppose that it is true, it meaning the equality, it is true for n, consider it for n plus 1. So for n plus 1 we would have f2 plus f4 plus and so on plus f2n plus f2n plus 2, and on the right hand side, so we need to prove that this is equal to f okay, it would be 2n plus 3 minus 1. Okay, so we start from the left side. So f2 plus f4 plus and so on plus f2n plus f2n plus 2 is equal to, So we notice that all the terms except the last one, this is exactly the left side in the equality for n, right? And we know that it is true by inductive hypothesis, so we replace it with this, with the right side. So we write that this is equal to, so this is by inductive, okay, by inductive hypothesis. So this is equal to f2n plus 1 plus f2n plus 3 or plus 2, f plus 2n plus 2. Now this can be simplified further because these are yeah, there is an error. Okay, so because I didn't write correctly the right side, so the right side here is -1, so fn plus 1 minus 1, so I didn't write the -1. So here we say that it's fn plus 1 minus 1, like this, plus f2n plus 2. So 2n plus 2 comes from here. We rewrite this term as is. So now we simplify it. So we write that this is equal to f, group it in different ways, so 2n plus 1 plus f2n plus 2 minus 1. And now here we have the sum of the two consecutive Fibonacci numbers, and by the original recurrent relation, we know that this should be equal to the next Fibonacci number. So this should be equal to 2n plus 3 minus 1. So now we look at the beginning and at the end. So we started with this, and we ended with this by the chain of equalities. And this is exactly what we needed to prove. So this is the equality for n plus 1 that we needed to prove. This is exactly what we got. So this concludes the inductive steps and concludes the proof.